No, but it is practical, because spherical, of course, maybe it was designed as an anecdote.
I still think it's more hilarious.
Sign is different account. Oh, candies. Of course they are on the center. Feel free to take them. I think someone left them for us. And at least I want to believe so.
I'm under the, if you don't know where it comes from.
Sealed Laffy. They're sealed the Laffy Taffies.
The heck can have a needle with some syringe? Put it in.
That'd be pretty devious.
Exactly. You wouldn't expect it.
It sounds like it's well thought out plan.
But would you expect that?
No, and I don't think anyone would do it unless they had the intent of doing it.
Maybe,
For someone in particular.
maybe they put laxatives in it.
Well, that's the kind of joke you gotta be around.
It's actually illegal.
Is it?
Yeah.
No.
Is it? Like if you made food and it has laxatives in it, you can go to jail?
And with the intent of quote unquote poisoning someone, yeah.
Laxatives just make them.
T-nice mixing.
Okay, we should not talk about laxatives now that we're on the record.
Haha, nice tea. Okay, better. Now we do have our display here too. Well, thank you for coming. It's so great to see you here. I don't know how long you will stay here, but definitely not the full length. So you will accumulate some minutes for your other projects. Who we are, what are we doing? We are in computational chemistry class. We did scare a visitor yesterday, so he wrote an email that I will not come to the class. It was a rotation student who has seen me for the first time. And I thought, okay, come on and do everything what graduate students do. Probably, I don't know if he will come ever again.
He has to.
Okay, good.
Otherwise you can give him a bad grade.
So I do not need to be nice to him.
Do you want him to join your group?
Huh?
Do you want him to join your group?
I do not believe that he will join the group.
Well then,
Well then, yeah, go
And
ahead.
you do whatever you want.
So, the goal of the course is to develop a set of skills to accompany experimental research with some computational model, right? We know how to build models, we know how to compute electronic structure, build orbitals with Hartree Fock. Now you know density functional theory. You are one inch from being certified experts in this theory, almost. We getting exhausted from writing formulas, although they need it. But main goal is practical skills that you come by your free will to study at the labs. And in a week from now, literally a week from now, with precision up to a minute, you will present some materials on the how to practically do calculations with vast software. I hope no one objects and everyone knows the subjects that you're going to share. For the theory materials, we are almost done with DFT, and we are a little short in time for practical skills and research. but we are a little ahead regarding the theory. So we can sacrifice maybe 1 or 2 meetings to, instead of going quicker, to going deeper, or just to chat and maybe speak a little bit more about practical skills. And another aspect where we are a little behind the original plan are homeworks, because even there is no pressure, you all do it for your own pleasure and for your research, but if we miss some of the skills, you will feel not at full functionality. So therefore, we spending a little time, a little additional time with homeworks. So I plan that for this weekend you will be entertained with another heavy homework, equivalent in its heaviness with the previous one, maybe a little lighter, and it will be based on the stuff that we did in the lab on molecular dynamics and movies, and some additional things that we didn't have chance to go over, but I will show today. Those are simple things, and everyone who completed previous homework will be able to do next one. It's just a little time investment. So with all these conditions and byproducts, we still have a central stream of the course of getting theoretical background for right theories, and we should slowly lean from ground state theories to excited state theories, because some of the materials that you explore are often excited by light, by applying voltage, or by some, I don't know, exotic perturbations. So it's good for the whole month to study excited state theory, and primarily it will be extension of the density functional theory, so-called time-dependent density functional theory, which doesn't have time dependence. Time dependence is just a convention, historical convention. Any objections on the general navigation? Okay. So last time when we were here, we have experienced an epic fail that we will not tell to any outsiders. We were trying to build the flowcharts of density functional theory, and it was observed that not too many of us placed sufficient amount of correct equations in this flowchart. This means that I'm failing as an instructor. Ideal assignment should be designed in such a way that everyone completes it 99%. So we will repeat this assignment until everyone gets it completed. Well, how else can we do? But I promise that you will not suffer and you will enjoy it. So prepare for a little childish surprise. So, in 2 minutes. First minute, you get scared. You see the flowchart that we didn't feel sufficient. If you know how to feel it, go ahead. It will be an heroic feat worth of extra credit.
Oh.
You can call it quiz, but I don't care about grades. I care that we all are on the same page. And as independent researchers, you will be able to write first author papers with accent on theory. Now, I want to provide you a little help. So first person already started laughing.
That's a lot of ink.
Yeah. Yeah.
A lot of ink. I know this one.
So I think this will make your life a little more pleasant. So what we are trying to do is to fill the flowchart, which is main principle of today's civilization in respect to atomistic calculations. So all practical, like vast majority of all calculations are done with functional theory. People who were awarded
Does
Nobel.
this mean gas?
Huh?
The density, is that?
Yes.
Okay.
Yes. So it is worthwhile to try providing correct stuff here. So put your name and the round blocks are for input and output. So before one starts cycle, one needs to insert a guess. So since it is a density functional theory, one needs to start with the density. Good? What is the expected output? Why do we bother to do this theory?
To get your total energy.
Yes, to get total energy. So our output is total energy. When you do your atomistic models, what are you starting with? What do you set up in your input files?
Ionic position,
Yes.
charge multiplicity.
If you know how to do it. Well, charge. And it is what we will discuss today in class. How to set up charge, which means number of electrons on the language of the WASP software. And then there is a criterion of tolerance limit, because these infinite cycles cannot be infinite. They need to be stopped somewhere, right? Are you done with cutting, pasting? So I'll collect it, put your name, and then I'll continue pasting it myself. Well, let's do one more together, and then I will collect. So when do we stop our cycle? Not we, but the software that we are running. When it does reach tolerance limit, when the calculation of total energy on previous and next step and code becomes smaller than tolerance limit. So when you run Gaussian, your tolerance limit is hidden somewhere very deeply and you never change it. They put it so small that every user will be happy with it. So it's like 10 minus 7.
You can change it easily though.
Yes, but it is not exhibited for first minute user. In WASP, it is one of the primary keywords in the in-car file. And you will see that you can easily dump the level of precision, get less precise, but achieve quicker convergence if you don't care about super high precision. And is it right time to collect? Are you done? So now you have only 3 pieces left. Thank you. Oh, no, I'm happy. I have sufficient background to assign grades that I like to.
I did energy.
Yes, please.
1, 2, 3.
Because to get your height
Okay.
yourself a shortening.
So now if I have forgotten what to do, I can just look and take your works as a help.
I don't know. We'll see if I was right.
So
I did.
if the density is known as a guess or from the previous cycle, we can plug in density into functional, and functional can be converted into the potential. And actual potential sometimes is is also a functional of the density, and frequently it is immediately provided as an analytical expression. Right? LDA is rho to the power 1/3. Potential V of LDA of R and rho
Oh no, that's
equals
the Thomas.
some
Fermi.
Thomas Fermi
Is fast.
is kinetic and 5 over force for total energy. Total energy for LDA is 4 over 3. But if you look for potential, not total energy, then it will be rho 1/3. And I'm finding any excuse to avoid going to other functionals because they immediately occupy the whole board. Maybe I will postpone it to Tuesday. But I have to present it, at least for information. Then, when we do have potential as function of the density, it is one electron potential, one electron wave function that allows to find these Cohen-Sham orbitals. And then these Cohen-Sham orbitals are used to build the total density by adding together all occupied orbitals. And here we see why do we need number of electrons. So we fill all orbitals starting from lower to upper until we have electrons in our wallet. Okay, very good. What do we do? We are fine. We were doing everything in the right way. No, let's keep the camera. So I think you will consider it as very childish homework if I ask you to do it once again without these stickers, as something to do at home without rush. And be prepared that one day we will need to write a little paragraph explaining this procedure. Explaining this procedure by human language, so that we can present it to people who work in the theory for 30 years, and they will recognize that you belong to this community. So it is like a password while entering military camp. You need to know the code word, otherwise you will consider it as not belonging here. Okay, but this is not the whole homework. There is a hard stuff, and I realized that I will fail to appear here in time if I will type it in. So it will be distributed as handwriting, but maybe following the meeting, I will type it in and deliver it in a more presentable way. So, and the homework is superior compared to all theoretical materials and anything we speak here, because it gives you actual, you are practical skills. So by now, you do have skills how to run molecular dynamics, how to place your molecule on a thermostat, how to let it cook in a heated state for certain time, and then I don't know if I need to show something and explain. I will be just staying in front of this polygon pointing on the things. So we were dealing with ground state configurations for the molecular dynamics we were dealing yesterday. As you probably got accustomed, each homework includes a request to go over all models that we have. Enough. We are going to do such hard things that it will be not physically possible to do next assignment for all models. So next homework will be dealing only with trans-polyacetylene to make it feasible in a reasonable time. But in addition to ground and neutral, we will look on the ground state cation when we remove 2 electrons, ground state anion when we add 2 electrons, and for first excited state from HOMO to LUMO. So for all of these 4 configurations, we are going to run 2000 K molecular dynamics and then report changes in the electronic structure. So if you take the geometry that has been developed upon molecular dynamics, take as a single point calculation and plot density of states and absorption spectrum, you will see the spectral signatures of heating. We can anticipate that something will happen to the molecule. Mostly expected thing is that if we do have bond breaking, if you have formation of radicals, then gap will decrease and it will start absorbing at smaller wavelengths. But we do not know it for sure. We need to check and justify it. So practically what we do upon heating and molecular dynamics for each of those models, well, there are two options which are equivalent. I would prefer to take resulting quant-car of molecular dynamics into new directory, name it postcar, run single point NSW calculation, and then generate density of states and absorption spectrum. Alternatively, you can just scroll through out-car of molecular dynamics and take the last list of orbitals and use it to generating density of states. And as VASP is running, it continuously saving wave car. You can do it either way. So, what do we report? 16 pieces of information. So there are 4 models and 4 pieces of information for each.
Is there only 4 models?
Well, there is one model in 4 different electronic configurations.
Oh, okay.
And for first configuration, we are almost done. We did it in the lab. But we do in 3 configurations more. So for each configuration, I am asking you to send me a link to YouTube video of the molecular dynamics. And you may realize and write little observations what you see. Like if it is anion or cation, it may change different pattern of dynamics. Or it may, like in neutral, it can stay intact, although moving vividly, but in the anion and cation, it can start fragmenting. So it's a little curiosity what will happen. Then image of the geometry before and after molecular dynamics, density of states before and after, and absorption spectrum before and after for each of the models. Please send me emails if something is problematic. It's the best part of my life to answer emails about this subject. But
it might change on the last three. I don't know where you put the number of electrons.
Very. Do you hear what Levi's verbalizing? What he's talking about? You can repeat it. It's very valuable information.
So we might not be able to use the same incore because of the fact that we're changing the electronic state. So we're adding 2 electrons, taking 2 away, and then we're also artificially promoting an electron from the HOMO to the LUMO, which I don't know if you use the same incar as it, or if it goes into the postcar. I don't know where it goes. Or you might need a new file.
So now it is not a regular lecture, but it is more like extension of the ground. 9, 10, and excited. So in ground, you just repeat whatever you did. Basically, you use your already available data. But when you run ground state calculations, the software understands which model you are working with, how many electrons are available from each nuclei, and what is the correct number of all electrons. Like for carbons, it counts that carbons have 4 electrons because it neglects 1s. For hydrogens, it counts as 1. So number of carbons times 4, number of hydrogens times 1. But we do not need to count it, because if you go to 200 atoms of different elements, we are getting tired of this little exercise. Although we can do C4H4, which means 4 times 4 plus 4 times 1. 16 plus 4 will be 20 electrons, right? And number of HOMO will be 10, because 2 electrons per orbit. But instead of doing this little exercise, we can request so it is a keyword out card. So it means that extract the line from the out card that contains this keyword. And this variable, this keyword, corresponds to number of electrons. So after you hit enter, you will get something like n elec equals 20.000. Because for density functional theory, electron is not a single piece. We can consider half of electron, third of electron. The theory doesn't care. If you can set up fractional number of charges and it will work perfectly. Although some of the reviewers of the papers may object.
Wouldn't that mess up with multiplicity?
No. Multiplicity, it will be too much for this homework. We already
does VAS automatically calculate multiplicity?
No.
Okay.
We cannot do everything at once. When we meet on coming Wednesday, just a night before presentations, I know that at least 3 of you selected the subject that deals with multiplicity, and we will need to cover it. So prepare, we will have intense time. Wednesday night learning, Thursday morning presenting. A couple of hours in the night to complete the presentation, but for 3 minutes it is possible. If you are so curious, there are additional keywords, and you can probably start preparing your materials. So, what is the name of most popular cell phone in this country?
Samsung?
And second popular?
Apple?
But what is the name of the product?
iPhone.
Yes. iPhone. What is the fancy machine that cleans carpet?
Carpet.
Or the
Vacuum?
Asimov novel of 1950? I, Robot. It's
Oh, okay. Yeah.
science fiction. I, Robot. So if the developers of VAF software were aware of this, and if they had a sense of humor, what would you think they using for keyword for calculations with spin?
Excellent.
Spin. So you need to I spin equals 2 to incar, and then you enable spin polarized calculations. But then it will find most appropriate multiplicity. Singlet, doublet, triplet, quadruplet. But if you want to enhance specific multiplicity, you need to change the keyword to error. It will be boring if I just give it to you. Remember what you were doing last meeting here. We were developing some minor theoretical background for spin polarized density function theory. And we agreed that for alpha and for beta spins, there are separate densities. And if we integrate them, we get number of alpha electrons and we get number of beta electrons, which do not coincide. And the difference between them, number of alpha minus number of beta, is a spin polarization parameter, which is 0 if it is singlet, 1 if it is doublet, 2 if it is a triplet. So it is number of spins up minus number of spins down. So if we are developers of the software with a little amount, with some amount of sense of humor, which keyword would we use? Number up down.
Oh, my.
And then you set it up to 0, 1, 2, 3, whatever you need. But you twisted my hands. You induced me to tell this. This is too much. This is not part of the. I would be happy if you do 32 calculations more for polyacetylene, looking how it changes if it is in different spin configurations, but it is not possible. Let's focus on singlets only. Even number of electrons, singlets, and therefore I'm suggesting 2 plus and 2 minus. So we do not touch doublets. Otherwise, it will be just too much for our learning curve. One can load more than capacity. So we get this number. And then, upon learning this number and writing it into our recordings, we can modify the incar for anion. In the incar file, we can explicitly write number of electrons, and then we just copy paste from here and increment it by 2. So it is, although anions means negative charge, but number of electrons is positive, so a bigger number. Bigger number. What do we do for cations? And please do not forget to include this line in every incar you are doing. It will not be stored automatically in the file with coordinates. If you do heating, you add this into heating. If you do molecular dynamics, you add it into molecular dynamics incar. If you do single point calculation afterwards, you add this line. Otherwise, it will bring you back to the neutral sigma.
Where do you add the line?
It doesn't matter.
Oh, good.
It is not user-friendly, but it is intelligent enough to see that if you swap keywords by the order, it is the same.
Okay.
You know, human languages have different structures. Like in English, I, am, I are different. There are many languages where it doesn't matter. It means only the grammatical form. And so I think they went this way. So the idea is that if you take the languages where the position of a word in a sentence doesn't matter, it means like you write flashcards, put them in a hat, toss, throw, and put it in any order, but the content of the message doesn't change. Their connections are indicated by the affixes, prefixes. Excited. So I know that one individual in the class has read textbooks ahead of the class material. Anyone wants to tell us in lay language what is configuration interaction? I can point camera.
So CI, or what Dimitri said, is you pretty much take electron using a Slater determinant and you artificially promote that to an unoccupied molecular orbital. And if you are in the regime of single excitation, you only excite one electron up. If you're in the regime of double, then you take 2 electrons, triple, and so forth until you get to full CI. And you do that for every configuration in there. So if you have 2 and 2, you would do a single 1 up, and there's, from your HOMO you can go LUMO and LUMO plus 1, and then HOMO minus 1 you can do LUMO and LUMO plus 1, so then you have 4 Slater determinants for your single excitation.
Make sense? Or it was like something not from here? No, just promoting electrons, right? Good. Let's return to our board. So you do have ground, and just for being a lazy drawer, I will forget about spins and put spinless electrons as a little circles. So for the, or we can consider circle as 2 opposite spin electrons. So ground state all occupied and excited when we remove 1 electron from here and put somewhere in the unoccupied orbit. So nothing here, something here, something here, something there. Make sense? And then our definition of the total density will change. Because the, well, definition by words will not change. Total density is summation of all partial densities of all orbitals which are occupied. And if we stop occupying this, let's say, HOMO, then from total density we need to subtract rho HOMO. And if we add electron to the LUMO, we need to plus the density in the R, rho excited. So this is probably the least precise, simplest possible approximation for excited states. It is in part corresponding to configuration interactions singles. Do not mix the words. Not singlets, but singles. Singlets as for spin configuration. Singles are for number of excitations. Single excitation. So if we redo our Kohn-Sham procedure as we did on this address sticky notes, Grand Rapids, Minnesota. No, I will not answer. I was going to answer with playful voice like, I'm on the lecture, why are you bothering me? If we replace the original expression I equal from 1 to homo, rows at I of R. So this is for ground state. And if you replace this definition of density of states with the new definition, so we skip homo and we add homo. And then repeat everything, same DFT procedure. It will be zeroth order approximation for an excited state. If we are going to predict excitation energies and compete beyond the cutting edge, no. It's only the qualitative approach. But if you want to observe changing of interatomic forces due to excitation, this is a qualitatively okay. And our goal is to see the response of the material to heating and to excitation. So if we modify our density function code with this little change, we just redefine the procedure to compute total density, and then use the same code. The energies will be different, tensions will be different, orbitals will be different, total energy will be different, and therefore, gradient of total energy determines forces. Therefore, forces will be different, and molecules will start reacting in a different pathway. Any objections to this little equation? So let's develop a little further. And I was writing these big ugly letters and used all the space. I'm going to erase, keep only these two, and develop them a little bit more. This will be quick, simple, easy, much easier than the stuff that we typically do in class. I'm going to open this ground state and excited state equations in the simplest possible way, without summation sign, just explicitly adding together. So row ground state, row 1, row 2, plus row number of electrons minus 1, plus row homo, and all of these densities, they are functions of position. Those are actually bar charge files that you are generating, and you are plotting on the homo and lumo, but you have seen that they all are generated and stored. And we can consider it as having the one factor in front. And then we can continue and write all available orbitals, rho n plus 1, which will be lumo, plus rho n plus 2, plus total number of orbitals, but they are multiplied by 0. 0 times, 0 times, 0 times, right? So we're including all orbitals, but those which are not occupied, they are contributing with 0 weight. if I would do it on the screen, I would just copy paste this expression. But since I'm on the board, I will just do a silly exercise and rewrite everything. And then just erasing a couple of symbols and going to excited state. Number of orbitals. We are developing density for excited state. And we originally, I'm going to reproduce and then change. 1 plus 1 plus 1 plus 1 plus 0 plus 0 plus 0. So how do we model promotion of electron from occupied orbital to unoccupied? Promote an electron from occupied to unoccupied. And we taking the simplest possible excitation from HOMO to LUMO. So we are taking the electron from here and placing it here, right? So instead of 1, we are putting here 0. Instead of 0, we are putting here 1. Good? Objections?
So these are electron.
As soon as we go further to the spin configuration, one can fix it. So, but if we are dealing with singlets, let's assume that we are exciting 2 electrons simultaneously. It's not the best way, but otherwise it will be too much complications.
Then shouldn't you have n divided by 2?
Or
N divided by 2
n divided by 2.
for your
number of
indexes, for number of electrons.
Number of orbitals.
No, no.
So
For HOMO or LUMO, shouldn't that be n divided by 2?
yes, we can count it as n divided by 2.
Okay.
Yes. If you count number of electrons divided by 2 is equal to HOMO. Good. But if you start writing divided by 2, you'll get crazy.
No,
N minus 1/2.
no,
No. Let's.
Yeah.
There is a way to address it very rigorously in the next step. But it will be too much if you do 2 of these challenges at once. So you are to add something.
Is it n orbital or n plus?
N
Because we
orbital.
already used.
This one is n orbitals. When you set up precision criterion, there is an automatic procedure that selects how many orbitals to treat. Since they are unoccupied, they do not contribute to density. It is not very critical, but the larger the number of unoccupied orbitals, the higher the precision.
Yeah, but is this n and that n is the same number?
Number of orbitals and number of electrons and number of HOMO are different.
Yeah, that's what I'm saying. It's just 2n. So
N or RB is
Okay.
number of orbitals. If you start requesting specific number of orbitals from VASP, it will fight with you and will try to argue and tell that no, I am offering something better. You haven't seen the output messages from VASP. Sometimes they are not very friendly. They tell in I wouldn't say rude language, but a little like, I'm sure you do not know what you're doing. Something like this. If you read output file or what comes to the command line, sometimes they give some suggestions or just tell them, okay, I will do what you ask, but it is the silliest possible thing. community, have supported this change from motion of an electron from occupied to unoccupied. Now, how do we communicate this idea to the software? Which keywords do we use? And it should be generic enough to be applied to any pairs of orbitals, to use any configuration and interaction single. So any pair of orbital as a representation of the excited state. So we need to count total number of orbitals. Better color. So this is total number of orbitals. This one is total number of unoccupied orbitals. Maybe you can call this one X, this one Y, and this one, let's keep it an orbitals. So we have X orbitals occupied by, in ground state, we have X orbitals occupied by one electron. And Y orbitals occupied by 0 electrons. Okay? I'm not telling keywords yet, just the logic. So if you want the keyword for modifying occupations of orbitals is, let's guess what is the keyword. We did cover it in class. If we have the occupation of an orbital as function of energy,
I Fermi?
very close. Fermi. But since those numbers 1 and 0 are weights,
W Fermi.
very close. You should seek for a job at the University of Vienna and become one of the developers of this code. They are constantly hiring, they have a big team. So Levi suggests weight Fermi. Very close. Fermi weight.
I thought the order didn't matter.
So Fermi weight. Fermi. So you type Fermi equals and then 1 multiplied by x, where x should be number of your occupied orbitals. Number of electrons divided by 2 if it is in empty space, and then 0 multiplied by number of unoccupied orbitals. If you mess up with these numbers, it will fail to work. So you need to count number of orbitals before you give this command. And this is a silly command because it will reproduce ground state calculations that will go anyway, automatically. This is a shorthand notation that we are going to use. But if we play with small molecules like H2, or whatever smaller than benzene, they allow the following syntaxes. You can write the weight equals, and then write 1 space, 1 space, 1 space, x times, and then 0 space, 0 space, 0 space, y times. To explicitly put the occupation numbers for each orbital. And you can put 1/2 if you need to.
So then to promote one from HOMO to LUMO, would you just say 0 for n
Exactly.
minus 1?
You place 0 here and 1 there.
But if we have a large one, can you do 1 times x minus 1, plugging in the number 0, 1, 1 times y minus 1?
Yes. Can you go to the board and write it down? Slower. we clean space. Yes. Exactly. So, thanks to Levi, now we know how to do the homework. We know how to entertain ourselves during the weekend. So, for the force electronic configuration for minimal excitation, we need to add into our in-car file this record. Fermi weight, and then this string that for specific model with 20 electrons and HOMO equals 10, it will be 1 multiplied by 19 space 0 space 0 1 space, and here one still needs to look into the out-car file and look for how many orbitals were available total. Suppose that there were total 20 orbitals, then here will be 9. But you need to double check. If the wrong number is provided here, VASP will refuse to run. Complain to me. I know what to tell to the whole.
So if you only want a single electron excited instead of a double excitation.
Then you need to go to spin polarized.
Okay.
If you do half of an electron, code will work. Code will not object to this opportunity. This is completely fine for density functional theory, but for scientific intuition, it is wrong. Because if you do, right now we have pairs of electrons, and if you take half of the pair of electrons, then it should have spin. And the energies of orbitals for different spins should be different. So the main practical reasons to deal with spin polarized DFT is, as you have already seen in Gaussian calculations, that in singlets for up and down, we have the electrons are sitting on the same orbitals, right? We writing energy HOMO -1, and we place 2 electrons in one orbital. This is completely wrong for non-singlet states. This is almost not observed. As soon as you promote one electron, or you just remove one electron, or have number of occupied and unoccupied different, it gets to drastically different energy levels for alpha and beta electrons. So for alpha, it is one energies, for beta are different energies. Therefore, we are plotting separate components of density of states. So if you want literally promote one electron, it is very dangerous to use singlet approach. One needs to, well, if you do not care about science, if you just cynic seekers of career, then we just worry about going through reviewing process. And if there will be a knowledgeable reviewer, he or she will not allow it to come through.
I have a question regarding this. So for that example, we have 20 electrons in that example, right?
20 electrons,
Yeah,
meaning HOMO equals 10.
Yeah, but if we promote the electrons, we should have the 20 electrons after promoting, right?
Yes.
So
This number 1 means 2 electrons. We are promoting 2 electrons, electron hole pair.
okay.
In this approach, if you do half of electron, it's not healthy.
So
It's less healthy than promoting 2 electrons simultaneously.
So what happens if we approach temperature that breaks, makes the Fermi distribution not a step function?
then it is fine, because it will not modify one orbital, but all orbitals will have continuous distribution.
Okay.
And at such temperatures, the gap most likely will disappear, and we will stop caring about individual orbitals.
And the 9 means 18 electrons, right? That means
Yes. 9 means 18 electrons. Correct, yes.
Okay. So then we have 40 electrons there, but here we have.
Oh, 20 electrons.
Okay.
20 electrons. 18 electrons are staying on their places. 9 pairs, 18 electrons staying on their places. Then one orbital is empty. We removed
Okay.
up and down.
Okay. Yeah.
Put it on the next, up and down. So total 9 plus 1 equals 10, multiplied by 2 equals 20.
Okay.
Okay?
Yeah.
Is this in the in card?
Ah.
You put this in the in card?
Yes, always. When you need to do excited state. So for heating, for molecular dynamics, and for single point calculation. Here is something that you already have. It is just a reminder what are our plans for coming Thursday. So let's see what we have and how far we are. So Faisal is not here. Oh, he wrote an email that he's on the conference, but what he plans to present is already covered. Vast output visualization of Kohn-Sham orbitals. We know it. Periodic potentials, momentum effective. Well, we didn't cover potential and effective mass. I probably tell about it as last thing after we get the rest. Whitney, density of states and orbitals for neutrals is what we already did in the two homeworks again. Anions, cations, excited states, it is what we will do this weekend. So it will be tightly related with what you present. Zach is in the hard situation. Well, Aaron is in harder situation because, but we will cover it on Wednesday, and then you need to relax, accumulate forces, and then make a spike of activity on the
That's
Wednesday.
typical, it's fine.
Thank you. But it will be this I-spin stuff. Light to matter interactions spectra for singlet. It is what John presented, so it should be no problem. Light to matter interactions spectra for doublet, triplet by LASP. Levi in the same level of hard situation as Zach, so it will be last minute preparation. I could present it now, but it will be just too much for us to percept at once. Sam here, modeling molecular dynamics or above room temperature, thermostat, so it is heating. Continue, good, all available. Job, continuation jobs from heating to molecular dynamics. So most important to copy Concar into postcard, otherwise nothing will work. Some of you have faced this error. Tracking temperature. It is what we were doing last night. Good. Brandon, practical steps to create, publish a movie based on molecular dynamics. So it is what we have recorded last night, how to publish it on YouTube. So we need to cover the spin polarized and momentum. Other than that, we are ready. Well, each of us should spend a little time to putting together slides But in principle, we are 70% ready. If like all subjects are 100%, then there is a third to complete. Let me just quickly skim through the slides, but probably we do not have time to focus on them in more details. I think this little scratch on the blackboard was more important, and we just need to cook this information. See, so when we meet on Tuesday, I will tell a little bit more about explicit functionals, which I hate. We need it as general part of education, but I do not know them from the top of the head, and I cannot request it from anyone to know from the top of the head. The general idea is like in Taylor expansions of functions, zeroth order is value of function at equilibrium point, and first correction is derivative times increment. Same for density functional. LDA meaning we take functional at one point, and next step is taking functional derivative, which gradient of the density, and take it as a second order correction. And it is what most functionals do. I will show some slides or sketch something on the board, but not now. Not now. And we started to talk about single excitations. So as we complete presentations, the rest of the course will deal with T, D, D, F, T for the lectures, and research projects for the final is a bad word, for free view last presentation in the class. And we will take into account free will of everyone, but it should be based on WASP and molecular dynamics. I think most of you can make this connection. If it is catalytic reactions, reactant approaching, catalytic center, and product departing, it's very well suited with molecular dynamics. If you have quantum dots with shells at ambient temperatures, they perform some motions. If it is molecular beam, then molecular dynamics is primarily to see how the molecule attacks the surface and then either sticks in or departs. And soon we will make a sign-up sheet for the presentations, but too much. Let's focus on presentation number 3 first, and then think of the rest. We already went through this list. And this is flowchart of our homework, and it will be flowchart of your research projects if you have no idea what to do. Like some of you are big experts in specific areas and you have a research plan. But if you just take a model and want to explore it, then you select model, optimize geometry, find its electronic structure. On alternative path, you heat it, and then compare the material in the ground in the 0 Kelvin and thermalized, and draw some conclusions. We did this. We spoke about excited states. Here is our favorite Fermi weight, which can be 1, 0, or fractional in between. And this is too much. We'll go over this subject when there will be time for more discussions. Let me announce completion of the meeting number 24. We skipped 23 because in the continuous line, 23 will be presentations. So completion of the meeting number 24. Thank you for attending. Please feel free to email me as frequent as needed regarding the homework. I realize that it is challenging and it takes a lot of your time. If you have forgotten to email me previous homework, please do now. Even if it is incomplete, it's better to remove this roadblock from your practice, because you need to put all your effort to the new homework. Whatever is done, I will just make as much credit as possible for attempt. Thank you. Meeting is dismissed.